Google Research quietly published a piece of mathematics that makes an AI's memory up to 8 times faster to use and 6 times smaller to store, with, according to their benchmarks, essentially zero loss in quality. The internet immediately nicknamed it the Pied Piper algorithm, after the fictional compression breakthrough from the show Silicon Valley. Except this one is real, it's peer-reviewed, and it's already spreading through the tools you use. Now, you may have seen videos about this already. They told you it happened. Almost nobody has explained how it actually works, why it shouldn't be possible, or the one detail in this story that most of the coverage got flat out wrong, including who actually built the viral demo everyone keeps sharing. That's this video. The real mechanism, in plain English, no equations on screen, you'll need to pause. And by the end, you'll understand exactly why this matters for the AI running on your own machine. Start with the problem, because the problem is beautiful. When an AI model reads your conversation, it doesn't just process your words and forget them. For every single token, every fragment of text, it stores 2 vectors in every attention layer, a key and a value. This growing collection is called the KV cache, and it is, quite literally, the model's working memory of the current conversation. Here's the brutal part. It scales with everything. More layers, bigger cache, longer context, bigger cache, linearly. A big model holding a long conversation can burn more memory on remembering the chat than some entire models need to exist. One practical example from published engineering analysis: a 70 billion parameter model with its weights compressed to 4 bits fits in about 35 gigabytes, but give it 128,000 tokens of context, and the KV cache alone demands another 40. The conversation memory outweighs the brain. The obvious fix is the one engineers always reach for. Compress it, store those vectors in fewer bits. If the model is a vast library, today every book on those memory shelves is printed in glorious high definition, 16 bits per number, and the shelves are overflowing. Reprint everything in a cheaper format, and the same library fits in a fraction of the space. Simple. And here's where it gets interesting, because the community has been trying exactly that for years, and it keeps going wrong in a very specific way. In recent tests published in the llama.cpp community, the engine behind most local AI setups, compressing the KV cache to 4 bits, looked completely fine at short context, and then at 110,000 tokens of context, quality collapsed by nearly 37%. And decoding actually got slower. Compression that punishes you precisely when you need memory most. Why? Because of what attention actually computes. When a model decides which earlier words matter for the next token, it doesn't read those stored vectors like files. It computes inner products, dot products between them. Angles and alignments in a high-dimensional space, geometry. And naive compression is like photocopying a map over and over. Each copy looks roughly right, but the distances quietly warp. The individual numbers stay close enough, while the relationships between them, the only thing attention cares about, drift. Long conversations amplify the drift until the model loses the plot. This is the insight that makes TurboQuant special. And it fits in one sentence: stop trying to compress the vectors, compress the geometry, don't preserve every stored coordinate. Preserve the inner products that attention actually uses. One widely shared technical breakdown put it perfectly. Traditional quantization reconstructs the vector. TurboQuant reconstructs what attention needs. So how? 2 stages, and both are explainable without a whiteboard. Stage 1, shake the box, then use a pre-printed ruler. Real AI vectors are messy, some coordinates huge, some tiny outliers everywhere. Squeezing that mess into a few bits wastes precision on the spikes. So TurboQuant first applies a random rotation to every vector, mathematically free, changes nothing about the geometry like rotating a photograph, but after the rotation, something lovely happens, courtesy of a deep statistical result. Every coordinate ends up looking like the same tidy bell curve. And once every coordinate follows a known identical distribution, you don't need to study your data to compress it. The optimal low-bit ruler for a bell curve can be computed once, analytically, in advance. No training, no calibration, no looking at your data at all. The paper calls this property data oblivious, and it's why the method works on any model, off the shelf the day you install it. Stage 2, keep a 1-bit receipt of the error. Even the optimal ruler rounds things off. So TurboQuant takes the leftover error, the difference between the true vector and its compressed version, and sketches it using a technique built on the Johnson-Lindenstrauss-Lemon, Johnson-Lin-Den-Strauss, one of the most famous results in high-dimensional math. The sketch costs a single bit per coordinate, and it acts as a correction that cancels the bias in those all-important inner products. Compressed vector plus tiny receipt equals an estimate of the geometry that is provably unbiased. The errors don't accumulate in one direction, they cancel. Add it up, and here's the scoreboard, straight from the paper and the Google research announcement. The key value cache compressed to around 3 bits per value, down from 16, for at least a 6 times memory reduction with near zero measured accuracy loss. Attention computation up to 8 times faster at 4 bits on an H100, because the math runs directly on the compressed values instead of unpacking them first, which, remember, is exactly the overhead that made naive compression slower. And my favorite line in the entire paper: the method lands within roughly a factor of 2.7 of the information theoretic limit. Translation, Shannon's math says there's a hard floor on how well any compression can possibly do. And this sits close enough to that floor that there's barely any room left beneath it. That's not a better codec. That's approaching the ceiling of what mathematics permits. Now, the correction I promised, because this channel exists to get the details right. The demo you've probably seen shared everywhere, 31 gigabytes of vector search index, crushed down to 4, outperforming Face. Face is real, but it is not a Google product. Google Research published a paper and a blog post. The viral demo comes from TurboVec, an independent open-source Rust library that a third-party developer built by implementing Google's math for vector search. That distinction matters two ways. First, credit. An open-source builder turned a paper into the thing you can actually download, and they deserve the mention most coverage skipped. Second, expectations. There is no official Google TurboQuant download button. What Google shipped is knowledge, which frankly is the more generous gift, because now everyone gets to build with it, and everyone is. This is the part that connects directly to this channel's home turf. In the llama.cpp community, again, the engine underneath most local AI, there's active work right now on bringing TurboQuant-style 3 and 4-bit cache modes to consumer hardware, with community members benchmarking early builds on new hardware as we speak. Follow the thread of what that means. The single biggest tax on running big models locally with long context is exactly this cache. 6 times smaller conversation memory is the difference between my machine chokes at long context and my machine holds the whole codebase. That 70 billion parameter example from earlier. With compressed weights and a TurboQuant compressed cache, the whole thing, model plus 128,000 tokens of memory, fits on a single GPU in a configuration that previously demanded several. And for retrieval systems, a 10 million vector search index that wanted 31 gigabytes of RAM now runs in about 4. Laptop territory instead of server territory. The ripples are already visible in the research world too. The method has been adapted for protein folding language models, extended into shared cache systems for multi-agent setups. When a compression idea starts spawning a family tree within months, that's the tell that it's foundational rather than incremental. Now, in the tradition of this channel, 3 honest caveats before the victory lap. First, the headline accuracy numbers are Google's own benchmarks. They're peer-reviewed at a top venue, which counts for a lot, but the fully independent, warts and all community verification is happening right now in those open forks, not finished. Watch those threads. Second, up to 8 times faster is a hardware-specific number, measured on a flagship data center GPU with kernels written for it. Your machine sees the benefit only once your inference engine ships proper support, which is exactly what the llama.cpp work is building. But in active development and in your Tuesday build are different dates. And third, this compresses the conversation memory, not the model itself. It stacks beautifully with weight compression. That's the whole point of the single GPU example. But it's one piece of the efficiency puzzle, not a magic halving of everything. None of these caveats shrink the achievement, they just place it honestly. A genuine breakthrough at the paper-to-product boundary, arriving in your tools over months, not minutes. Step back, and there's a bigger pattern here worth naming, one this channel has been tracking from a different angle all month. The AI race gets reported as a race of scale. More parameters, more GPUs, more data centers. But the quiet counter race is efficiency. And efficiency is where the democratization actually happens. Expert streaming lets giant models run from an SSD, quantized weights shrank the models themselves. And now the working memory, the last stubborn, uncompressed piece of the puzzle, just got its breakthrough, published openly, free for every open source engine to absorb. Every one of these advances moves capability down the hardware ladder, from clusters to workstations to the laptop already on your desk. The frontier isn't only getting smarter, it's getting closer. So here's my question for you, and I'll pin it below. Context memory is about to get several times cheaper. What changes for you first? Is it finally running long context models locally, feeding an entire codebase into a coding agent, rag over your whole document archive on a normal machine? Tell me the workload you'd unlock. The most interesting answer helps shape where this channel digs next. Every source, the Google research announcement, the ICLR paper, the TurboVec repository, and the community benchmark threads is linked in the description so you can verify every claim yourself. That's the standard on this channel. If you want the math behind the headlines explained honestly, in plain English, every single day, subscribe. I'll see you in the next one.